Welcome back. So we have been discussing graph neural network, particularly graph convolutional network (GCN). And a quick recap: what we have discussed in the last lecture is that GCN is basically a message passing paradigm, which for every node it basically generates a computational graph, and the computational graph is driven by the topology of the graph, and for every node, right, we have a separate topological structure. We have separate computational graph, and we specify the depth of that computational graph, and we also have convolution operations at different places, right. Basically for every depth we have a convolutional operation, and in the convolutional operations we have two parameters that we train. One is W and other is B, right. So we discussed this equation, right. This is the very important equation that hidden state, right, at a particular depth or at a particular time, right, of a node V is essentially a function of the neighbors, right. We basically take the aggregation of messages from the neighbors. Aggregation, if the aggregation is just a mean, it is basically going to be h of u k minus 1, where u is the neighbor of V, and then we normalize it by the number of neighbors, right. And apart from that, we also have the hidden state of that particular vertex V, right, at the previous timestamp h k minus 1, right. And this is parameterized by Wk and this is Bk. We wanted to keep these two things separate, and Wk and Bk are learnable parameters, and the entire things will be passed through a nonlinearity sigma. Okay, this is the idea. And so for every depth we have separate W and V. For depth 1 we have W1 B1, for depth 2 we have W2 B2, right, which we learn. So these W's are essentially, you can think of this as neural network weights, right. For example, say you have this kind of network structure, right. You can think of the weights of these connections as W's, right. So you can think of it basically as two different convolution operations happening here at depth 1, here at depth 2, right. So now and we also discussed how we train GCN. We use supervised setting. For example, the task is node classification, or say link prediction. You basically come up with a loss, and let's say the loss is a simple cross entropy loss. So what we will say is that, say at the final stage, right, you have, say this is a computational graph, right. Okay, let's say like this, and say you want to predict whether this node is fraud or genuine. So you have some classification model here. This can be logistic regression, this can be a simple neural network, right, multi-layer perceptron type. And let's say the loss is a simple cross entropy loss, where you say that, okay, the loss is essentially right, like this. So for a particular node V, right, let's say you are doing it for a particular node V. This is y hat V. Y hat V is the actual label, right, actual label of V. It can be, say it can be 0 or 1, right, and you have the output. Let's say it's a simple let's say it's a simple logistic regression kind of stuff. So ZV is the embedding that you get, right, for this node at the final stage, and this theta is essentially the logistic regression parameters, right. So this is the parameter of the classifier. Remember, this is not the parameter of the embedding method, right. So and then you pass it through a sigmoid. This is basically logistic regression. Then you have a log loss, right. So this plus 1 minus this, right, 1 minus hat log of 1 minus sigmoid okay. And this loss is for a particular node V, right, and then you basically sum it up for all the nodes, right, all the nodes in V, and you then take the derivative with respect to each and every component of W and B, because W and B are matrices that you learn, that you want to learn. So, for every element of W and B, you take the derivative of this with respect to that element, and you back propagate the error, right. So, now this is GCN, normal GCN. There are multiple variations, as I mentioned, right. One such variation is called GraphSAGE, okay. So, GraphSAGE is essentially a more generalized version of graph convolutional network. Remember, the beauty of the graph convolutional network is that it can also be useful for inductive learning, right. I hope you have heard about something called transductive learning and inductive learning, okay. These are the very common terminologies in machine learning. These are two learning paradigms. So, in transductive learning, the idea is that let us say right, the test set is known to you, okay. Let us say you have a graph, right, and the entire graph is known to you, right, and you are say running deep work or node to way kind of approaches on the entire graph, right, and you get some embeddings, and you also know the labels. Let us say it is a classification problem, let us say you know the labels of some of the nodes in the graph, right, and your task is to get the label of the other nodes, right. So, from the labeling point of view, this is your training set, this is your test set, right. But remember, the test set is also known to you. Therefore, when you trained your graph learning, graph embedding method, you gave the entire graph as an input to the embedding method, right. So, that deep work, node to bake, these kind of methods are run on the entire graph, right, and you got the embeddings, right. So, you somehow use the topological structure of the test set as well to get the embedding of the train set, right. So, this is called transductive learning, when you know the test set also, the test set is known to you. In case of inductive learning, the test set is not known to you. So, you have to take the decision, you have to run all your learning methods on the training set, you generate some embeddings, whatever, generate some representations, and when a new test set comes in, you have to also generate the representation of that additional that test node, right, and you perform classification, okay. Let us say you have an evolving graph, right. So, you know the graph till t, right, and you have trained your embedding methods on these nodes, right, on the given part of the graph. When a new test set comes in, right, you do not know, because this node was not a part of the training set, right. So, if you use node to way kind of methods, how do you get the embedding of this unknown node? You can't do that, right. So, this is inductive learning. In the inductive learning, the test set is not known to us. I mean, if you think of a normal machine learning, right, kind of applications, mostly inductive learning, right. So, but inductive learning is difficult because you do not know the test sets, right. Now, think of a graph like this, right, and let us say your method has already been trained on this graph, and a new node comes in, this node gets attached to this node and this node, right. You have to run your method again, right, say deep work or node to wake on the entire graph, and that is troublesome, because think of Facebook, Twitter like networks which evolving over time. So, every time if you keep on running graph learning methods from scratch, you are gone, right. So, this is a terrible approach, right. What you can do here, you can use GCN, okay, because GCN, the two trainable parameters W and B, these two parameters are same across all the nodes, right. So, on the training set you can easily learn W and B, right. Now, when a test set comes in, this node gets attached to these two nodes. Now, for this node you basically get an computational graph. For this node you get a computational graph. Now, you know that for the computational graph for label 1 this is W1 B1, you already got it, W1 B1 is same across all the computational graph. So, what is your task now? Your task is just to feed, right, the representations of the neighbors, right. If the representation are not available, you just use either an identity matrix or identity feature, all ones, not identity, all one feature vector, or if the vector is available, feature vector is available, you pass it, right, first to W1 WB, W1 and B1, then you pass it to W2 B2 and you get the representation for this node. Okay. So, GCN is also suitable for inductive learning, right. Now, in GraphSAGE what they suggested is that you just take the same GCN paradigm, but in a different way, right. What you do here, now in GCN, let me just go back, remember this formula, right. So, in GCN what we do, we make it even more generalized, right. What we say is that the embedding of a node V at depth k or at time k would be something like this. So, in GCN we used some sort of weighted average, right, and weight was 1 by NV, weight was same for all the neighbors, aggregated then weighted, aggregated and then averaged, some sort of weighted average. So, here we make it generic, we are saying that let us use any aggregation method, okay. And what is the parameter and what are the arguments? The arguments are the neighbors, embedding of neighbors of V at time k minus 1, right. Now, this aggregation function can be mean, can be sum, can be mi and mean, can be max, anything, right. And let us make it parameterized Wk, and you have the additional part, right, which is H V k minus 1 Bk. Let us not sum them up, we are not taking the sum, unlike there in case of GCN where we just took the sum, here we keep them separate. But when we sum them, the information about the individual components will be gone, right. We wanted to keep this thing separate, therefore, here we concatenate them instead of taking the sum, right. This part and this part will be concatenated, comma, right, appended, then pass it to sigmoid. This is GraphSAGE, right. Although GraphSAGE was developed just to show the inductive power of it, right, but of course, GCN can also be used for the inductive learning, and GraphSAGE paper also theoretically show that what could be the possible aggregation operations that one can think of. The first one is just simple a mean, right. We have already seen what is it. It is basically this one, right. Right. It can also be just a sum, okay. It can also be a pooling kind of operation. It can be max pool, right, or mean pool. Max pool or mean pool can also be possible. They would also generate the same size vector, right. Max pool or mean pool of the neighbor embeddings till time k minus 1, at time k minus 1, right. Even it can also be an LSTM, right. It can also be another neural network like an RNN kind of network. So, along short term memory, you all know what is LSTM. What you do here is that you since let us say for vertex V you have 4 neighbors, right. you pass it through LSTM, right, and the final output would be the output of the LSTM. Remember, this aggregation operation should be order invariant, right, but you may ask LSTM is order variant, right, because if you change the order of the neighbors, it will change, it will produce different output, that is true. So, therefore, what you do if you really want to use LSTM here, you basically you know what you do, you shuffle, right, your neighbors multiple times. So, this is LSTM configuration 1, you have one sequence of neighbors, you get the output. You have LSTM configuration 2, another sequence of neighbors, you have with some output, and so on and so forth, and then you aggregate this output, right. So, if you shuffle multiple times and feeding and feed them to LSTMs, different LSTMs, and aggregate them, somehow that order invariant property, somehow can be preserved, right, that is the idea. You can use LSTM here. So, GraphSAGE turned out to be very useful, particularly in a network like Pinterest, right. Pinterest is also a network where you share images, and they showed an algorithm called PinSAGE, which basically uses GraphSAGE for Pinterest kind of social network, right. So, so this is about GraphSAGE. There are many things which I intentionally skipped, particularly the theoretical part of it. It turned out that sum is better than mean, right, particularly if you look at the aggregation, different aggregation operations, there are theoretical results showing that this aggregation is better than that aggregation, and why, right. For example, sum is better than mean. So, in the next lecture, we will briefly talk about another part which is called graph attention network, GAT in short. We look at how attention mechanism can be used for graph embedding. Okay, thank you.